lot about Taryn Lane, except for he's a graduate student here. And so I got up on the web and I said, well, I'll look and see what I can't learn about Taryn. Well, I couldn't learn much because the hyperlinks. I got back an error message that said we were down right now. Yeah?
When was this?
Could be because of our problem,
though. Replacing memory in the link. In the link to the outside.
There have been a couple difficulties with my web pages, so I don't know. That's like about 93rd down on my maintenance queue. So
No.
I know. Call it a security measure.
So let me give you a little. He graduated from Ballard High School in Louisville, Kentucky, and he earned an undergraduate degree,
Here.
electrical and computing engineering at Purdue University, and he is now working towards a PhD, and he's studying under Carla Broadley, which probably a lot of you know in ECE, has been associated with Gene Spafford's labs for the last few years, and he is currently seeking employment, as some of you probably are. I've already quizzed him as to where he wants to go and why, and he's still not sure yet. So I guess in terms of what Taryn's going to do when he grows up, he doesn't know yet. It's Taryn Lane.
Thanks.
You're welcome.
Well, good afternoon. Or morning to those of you who live on my schedule. Thank you for coming, even those of you who are required to be here. I should start by saying, that the talk I'm going to be giving you today is intended for a very general audience. It's very high level and somewhat abstract. I'm not going to get down into the grungy details of this work. If you would like, in-depth details, ask me or go see the papers. Feel free to ask questions during the talk. But there's not going to be time to cover everything. So, I'll start by telling you a little bit about the problem that I'm interested in. Some of you may be familiar with this kind of problem, but may be new to others of you. The problem that I've been working on for the past few years is anomaly detection, specifically at the user level. And so user profiling is associated with this. The goal here is to automatically infer a model of a user's normal working behaviors. And then we'd like to be able to detect deviations from this model, abnormalities, because these deviations may constitute some sort of hostile activity, which may be some intruder who's broken in and exploiting an account, or it may be the profiled user doing something not nice, abusing his or her privileges. In particular, I'm taking a user assistant model of this domain, in which the goal is to build a single detector for a single user that monitors that user's account. So I would like to have an assistant that monitors my account and is able to tell me when suspicious activity has been going on, when somebody maybe has stolen my password and is using my account. I'm interested in long-term attacks that span hours or days or perhaps longer, because I'm using a class of statistical techniques here. It takes time to build up sufficient statistics to be able to do any kind of real analysis. Short-term hit-and-run attacks, where somebody, say, logs into your account and just deletes everything and logs back out, that kind of thing is better handled with signature pattern databases and pattern matching on known attacks. And I should say up front that the sensor I'm going to be telling you about today is really intended as kind of a single sensor in a multi-sensor array. So those of you who are familiar with the aphid work here will be familiar with this kind of concept. You've got a bunch of different sensors monitoring different data sources and then integrating all of those data sources to yield a high-level decision. So the kind of thing I'm talking about today is a fairly low-level sensor that monitors just one data source, and that being one user's behaviors. Well, so why do we care about this problem? Well, for some of you this may be obvious, but for others, first of all, in a very practical sense, there's no such thing as perfect security. We can't build systems that no one can break into, and even if we could, probably nobody would use them. They're all too busy off using Windows NT. And yet, in spite of this, we're all the time seeing more and more valuable and private data and confidential data being put on machines and being put online. The connectivity of the internet is growing just incredibly quickly, and a lot of the people who are going online now are home users or relatively, security naive people who may not consider the issues and may not know how to secure their systems. At the other end of the scale, we have sysadmins who are responsible for larger and larger LANs, thousands and tens of thousands of machines, and yet, often their support staffs are being downscaled at the same time. So we'd like to be able to do something to help these people out, and we're kind of taking a defense in depth sort of approach here, that the detection reinforces security, or reinforces the barriers. So if somebody penetrates the security barriers, we at least have a kind of backup that we can detect that something happened. And I should say that this kind of problem has been addressed at the network level, network intrusion detection systems, pretty steadily for the past 15 or 20 years. There's been relatively less work at the user level, watching user commands and user behaviors. There was some proposed work early on, but I haven't seen anything actually fielded, because this turns out to be a rather difficult thing to do at the user level. Okay, but I should add the caveat that I am, by training and kind of at heart, really a machine learning person. So what does this task look like to me as a machine learning problem? Well, it's fascinating from a machine learning perspective for a number of reasons. This is a task characterized by non-stationary data sources, or what we call concept drift. That is, the concept you're trying to learn, this normal user behavior, is constantly changing. People are always learning new behaviors, they're learning new commands and new ways to use their environment, and they're being subject to new tasks. Their environment is changing, and so we're not aiming for a single fixed concept here. So the system has to be capable of doing continual learning. You can't just train it once, turn it on, and let it go, and leave it alone. And yet at the same time, we have to be able to differentiate these kind of normal user changes from anomalies, from the kind of hazardous situations that we're explicitly trying to detect, which may also appear to be changes or concept drift. This is a domain characterized by single-class training data, or unsupervised learning. That is, rather than trying to build a model of a bunch of different users, say build a model of me and you and you and you and you, and differentiate between them, and especially build models of all of our intruders or imposters and differentiate among them, we're trying to build just a model of one user and differentiate everything else from that. And there are a couple of reasons we do this. The first is privacy. If I'm building a sensor to protect my account, you may not feel comfortable giving me examples of your private behavioral data, because even though, well, I am perfectly trustable, you don't know where that data's gone once it's left your hand, right? And so there are these privacy concerns. So we'd like to only train the system on data that's available from the one user that we're trying to monitor. But there's a second issue, and that is coverage. That is, even if we have examples of some intruder data and we build models of those intruder data, we have no guarantee that that's really going to reflect the next hacker to come down the pike. And of course, the system penetrators out there, at least the good ones, not the script kiddies, are kind of renowned for their novelty and innovation. So there's no clear-cut way to be able to say that what our model is really reflects them. So we'd really like to just be able to discard everything else. This problem is interesting because it deals with discrete temporal sequence data. There's been a lot of work on dealing with continuous time series data classification, but there's been relatively little on dealing with time series of discrete data points. And finally, we have to operate under resource constraints. Clearly a security system which obstructs the user because it sucks up too many system resources is not really going to be used. So it has to be resource conservative both in terms of space, although hard drives are cheap these days, and in terms of runtime, which is a somewhat bigger issue that I'll be talking about later. So this is pretty much an overview of what I've contributed to this problem, and it's also kind of an overview of the talk, and it'll show you the points that I'm going to be hitting. With respect to the machine learning community, this represents an entirely new class of problems to deal with. The security community has been aware of this anomaly detection problem for years and years and years. And as I said, they've been working on network intrusion detection for a long time, although there's been less work on the user level. But for machine learning people, it's interesting and new, and it introduces like all of these problems that I showed you on the last page and bundles them all together, which is a nasty problem. Each of them is difficult individually, but when you bundle them all together, it's a real pain, which makes it cool. So here are a couple of the points that I hit earlier. So I've worked on a similarity measure. How do you say that data you're seeing now is similar to data you've seen in the past? And how do you differentiate along that axis? I've worked on data reduction techniques. As I said, we want to be resource conservative, so we'd like to be able to reduce the amount of data that we're actually handling, which can save us space and time. I've worked on online learning techniques, that is, ways to adapt the model continuously as the user changes, have the model change. And something I'll be talking about at the end is a hidden Markov model representation of this problem. So these are kind of machine learning-ish contributions. With respect to security, as I said, this is a well-known problem, but there hasn't been a whole lot of work at the user level. So that's kind of an interesting thing, trying to get it out into the community there. And this kind of represents a whole new batch of approaches that I haven't seen people really try. And finally, I have to say that another contribution is performance evaluation. In a lot of the intrusion detection work that I've seen in the published literature, there isn't much in the way of performance evaluation. You can't really tell how well the systems are doing. They will give you this architecture and propose a bunch of features that they're going to be looking at, but they never really tell you what's useful. So I think it would be nice to kind of get a higher emphasis on performance evaluation out there. So I've examined a couple of classes of models for user modeling, and I'll be talking about each of them in turn. I know that these are kind of small diagrams. You don't have to be able to get the detail at the moment. I'll go into it more later, but I just want to differentiate the kind of classes of techniques I'll be talking about. So in the first one, I'm dealing with what's called an instance-based learner. And this learner uses a dictionary of exemplar behaviors and then compares new data to those exemplar behaviors. And the behaviors I'll be talking about are these kind of strings of commands, and I'll go into that a little bit more. But an alternative class of models is this hidden Markov model, which is a kind of statistical model of sequential data, which I'll tell you more about later. So initially, I spent a lot of time working on an instance-based learner, in which the user profile that we're talking about is, as I said, a dictionary, or just big collection of these exemplar historical behaviors. And the instances in the instance space, these historical behaviors are short fixed-length sequences of symbols. So you can think of them as being fixed-length strings. So we're talking about like 10 symbols at a time. And the symbols we're dealing with here are Unix commands and their arguments. Classification can be done in terms of proximity to historical data, where proximity means similarity between two instances. So if I have a new incoming data stream that I've never seen before, I can take a fixed length chunk of that, an instance, and compare it to my instance base one at a time in terms of a string matching function. And the value I get back gives me a notion of how similar that is, how close that is to things I've seen in the past. The string matching function that I'm using here is a custom one that I developed for this domain. I've tried a number of things, including stuff like edit distance and match count and things like that. But it turns out that empirically what worked the best was a quadratic string matching function. Basically, you look at the run length of matches between two instances, and you take a quadratically weighted function of those run lengths. And I should say that the initial profile, the profile that is used at the beginning of the testing phase is going to contain all historical data, all data that was available during training. And this is as opposed to the data reduction work, which I'll be talking about later, in which before we go into the testing phase, the training data is reduced and some is discarded. So here's kind of a data flow diagram of what the system is doing, and we'll go through this step by step. Up here in the upper left, in very small type, is the input data. This is a stream of Unix command lines concatenated together, so kind of undifferentiated, just stream of what you'd see on somebody's terminal. It's passed through a tokenization routine, which converts this into an internal format and removes file names. So here, if you can read this, it says cat bar baz. We have 2 files. This gets replaced with cat and a marker saying that there were just 2 files there. We do this for a couple of reasons. One is that this dramatically reduces the alphabet size. So when you include file names, sometimes we're dealing with an alphabet of something like 25,000 unique symbols. It's very hard to gather statistics on this. Data is very sparse at that level. When you remove the file names, it drops to about 2,500 unique symbols. So we're getting an order of magnitude improvement. But it's also interesting that what this means is that because we can't see the file names, we're really interested in, or the sensor is really looking at, people's behavior rather than content. We're looking at how you're modifying files rather than which files you're working on. This data stream is now compared to the historical profile. So this is the instance base I was telling you about via similarity function. This is the quadratic string matching function I was telling you about. And the output of this is a time series of similarity measures. So at each time point, we have a notion of how similar this stream is to this historical profile. Well, as you can see, this is pretty noisy. This is hard to do classification on. So we pass it through a smoothing filter and get this nice, much nicer, smoother curve out, which we can classify with respect to a threshold test that I'll be telling you about in a moment. And the output of that is a stream of decisions. So at each time point, we now have a decision as to whether what we're seeing is normal or anomalous. So then there's a feedback loop, which is used in the online section that I'll be telling you about later, which allows us to update the classification parameters or to update the profile as we run. But the work I'm going to initially be telling you about is entirely batch mode and takes place just up here. So this is how classification is done. I'm using a relatively straightforward decision theoretic approach. What we have here are 2 similarity histograms. So along the x-axis here we have similarity. This is how similar input data is to our historical profile. And vertically we have frequency. So what we did here was just gathered a bunch of data from a person, measured it with respect to the historical profile, and saw how the similarities fell out over time. So the blue curve is the profiled user. So this is the person whose historical data we were using. And this red curve is somebody else. This is the anomalous user or the imposter. And you should just I'm going to be using this same color scheme for the rest of the talk. So blue is always going to represent the profiled user, and red is always going to represent our imposter. So now we can draw a decision between these two by placing a cut point here on the similarity axis. And everything to the right of that is considered to be normal, and everything to the left of it is considered to be anomalous. So if we see some new data that measures a similarity at 20, we would call that normal. So the question becomes, how do we select this cut point? Well, in the decision theoretic sense, there's kind of an optimal thing to do, which is to select this intersection point. This yields what we call the Bayes optimal threshold. And it's optimal in the sense that this minimizes average misclassification over time. Unfortunately, this isn't really what we want to do in this case for a couple of reasons. One is that by assumption, we don't have this. We don't know what our enemy looks like, so we can't measure this curve, so we can't find this overlap point. But the second is that if we did put the cut point right here, you note that we'd have this huge area under here And this would be a false alarm rate. So in proportion to this area, we would be throwing false alarms. So you'd be getting like an alarm saying that you weren't you every like 30 seconds or something, which is clearly not feasible. So instead what we do is choose a threshold down here according to what false alarm rate we can sustain. So we start by picking a false alarm rate that people are willing to deal with, and then we can select this cut point to achieve that. Now clearly we've sacrificed all of this area over here under the red curve. All of these points will be misclassified as being normal, but we still have this region over here and the system is more nearly usable. So as I said, I've done some actual testing on this to see how well it works, and I'll be telling you about that. The first thing I should say about the data is that, I'm going to give you the caveat up front. I don't have any instances of real attacks to test this against. I've looked. About a little over a year ago, we asked CERIAS to put out a call to all of its sponsor organizations for examples of this kind of data, and none was forthcoming. And I should say that this isn't because the problem doesn't exist. This is because nobody actually keeps the data, because they don't know how to analyze it. What do you do with like megabytes of somebody's shell histories? I mean, nobody knows how to deal with it, so they don't bother to keep it around. But the problem, is clearly real. So what we can do, is look at data from known users and compare two known users under normal working conditions. So I can build a profile from one user's data and then test another user's data against that. When the other user I test is the profiled person. So I'm testing someone against their own data. This gives us an idea of how well the system is doing at recognizing the known user. When I test it against somebody else's data, this gives us an idea of how well the system is doing at recognizing an intruder or an imposter. Now, clearly this isn't the worst case scenario. This is not some sophisticated hacker sitting down trying to break the system. But what this does represent is kind of a naive attacker who's broken in, is unaware of the detector system, and isn't trying to defeat it actively. This may seem a little bit contrived, but when you consider the preponderance of script kiddies out there, if we could catch these people who are clearly naive, we'd be doing pretty well. So the data I'm actually working with is Unix command shell traces drawn from the C shell and the TC shell. I have two user groups that I've been examining. A group of data gathered by Greenberg at Calgary back in '88. And that's comprised of 98 users. There were originally 168 in the study, but I needed at least 2,000 command line tokens from each person, and only 98 of them had that much data. And then there's a group of users that I've been monitoring at Purdue over in ECE for the past couple of years, and I have a great deal more data from each of these people, but I only have 8 of them. Also, there's more types of people down here. We have, computer scientists and professional programmers, as well as novices, that is freshmen, and non-programmers, people who are just using the system, to read email or whatever. So the 2,000 tokens here represent one fold. That is, I can build one profile from each one and still have enough data left over to build a testing set. Whereas up here, because I have more data, I can do this 5 times. So I can build 5 profiles from this at different time points and have 5 sets of testing data available. And so I should tell you a little bit about how we actually measure performance here. How do you know when we're doing well? Well, there are a couple things you can measure. The first and kind of the most commonly looked at is accuracy, which is just a measure of how often, what percentage of your test set are you labeling correctly. So if the test set belongs to the profiled user, what's your rate of truly accepting that person? And when the profile or when the test data belongs to somebody else, what's your ability to truly detect your imposter? And the kind of converse error rates are false alarm rate and false accept rate. How often are you allowing an intruder in? But I'm gonna focus on this in this talk because it's easier to display and it's easier to talk about. But you should at least be aware that there's another way to look at this, and this appears in some of my papers, so you can look there if you're interested. And that is mean time to alarm. That is, what is the mean time between login and the time we throw an alarm? So for a real user, for the profiled user, this is a measure of how often the user is being bothered by the system, being inconvenienced. But in the case of our imposter, it's a measure of how quickly are we actually catching the imposter, or how much chance does that person have to do damage before we have an alarm thrown. So how well does it do? Well, here's some accuracy figures. These are accuracy histograms. So across the horizontal axis, we have accuracies. So from accuracy 0 over here to 1 up here. And vertically, we have counts of test sets. So this is this is the number of test sets which got 0 accuracy, and this is the number of test sets which got accuracy 1. Now, if you can see, you might notice that the vertical axes are different here. This goes up to like 20, and this goes up to like 6,000. Well, what's happening here is that this is on the Calgary data, which, as I said, had 98 users. So that means that we had 98 profiles generated, 98 chances to test against self. So there's a total of 98 points here. But we have 98 times 97 imposters. So for each user, we have 97 imposters. So there's a heck of a lot more data points over here. Well, kind of the base result here is that we're doing really well over here. We're doing great at catching our imposters. We got this huge mass up here and kind of just a little bit all across the board down here. We aren't doing so hot over here. We're promising. I mean, we have this very nice spike up here at accuracy 1 where we're doing perfect differentiation. And even we've got a lot of cluster of data up here where we're having pretty high accuracy, but there's maybe more points down here than we'd like. But there are a few things we can do to improve this, and a couple of them I'll talk about later. But one thing we can do, if you recall from the classification slide, you have these two histograms and a decision threshold that you can slide back and forth. Well, it's possible to slide the decision threshold kind of to the left to accept more data, which will move more of this up to here. But in doing so, we sell off some of this and we lose accuracy over here. But clearly, we're doing very well over here, so it may well be worth it to make that trade-off. Well, so that's how well the system does kind of straight up. But what about this issue of resource constraints that I mentioned earlier? Clearly people are subject to changing habits, and we have to be accumulating these new behavioral instances over time to reflect these new tasks and new behaviors that people are showing, which means that our profile size is potentially unbounded. This is a problem for a couple of reasons. Clearly disk space, but we're not talking about so much data that we're going to be overwhelming a 9 gig drive here. But what it does cause a problem in terms of runtime. Classification time is related to basically, k times like the number of data points squared or something like that. And so the more data you have in the profile, the longer it's going to take to do its classification. Now, if you're running this in batch mode overnight, that may not be a big issue, but if you want to run this in real time, in between every command that the user types, this is going to be an unacceptable penalty. So we'd like to be able to throw away some data. You can, of course, just do a straight up lossless compression, which will save you disk space, but isn't going to do anything for you in terms of time. Or you can do what's called feature selection, which means that for each of these fixed length strings, these instances we were talking about, you can go in and throw away some of the symbols in it and make the string itself shorter. And if you do this over the entire profile, you've removed a lot of data. But the approach I'm taking here is actually throwing away some of the instances in the profile. The first way I approach this problem is a utility-based instance selection. This means that we're trying to get a measure of how useful each point in the profile actually is, and then we can throw away the ones that don't look like they're very useful to us. And we can measure this with respect to some independent set of evaluation data, where this is gathered from only the profiled user. This isn't data from some other user, some imposter. And the particular measure of utility we're going to use here is in terms of locality of reference. The idea is that if someone has done something recently, they're probably going to do it again. If they're running GCC, 2 commands ago, they may well be running GCC again soon, when they fixed a couple more bugs. So you can do least recently used. You can look back in your data set and see which of these points was actually used for classification recently and throw away ones that haven't been used recently. Or you can use, throw away ones that aren't frequently used. Or you can just throw away the oldest things in the data set. Or of course, you can just randomly pick some to throw away. And the key point about this is that this method is employing a relation between data that's in the profile and some external data set. So how well does this work? What does it look like? Well, I've picked a couple of examples here to show you. What we have here are a couple accuracy histograms, or a couple accuracy scatter plots. And I've been told that these are a little tricky to deal with, so I'm going to go through them kind of slowly for you. We have the 2 methods, the LRU method and the FIFO method, which I talked about. I picked these 2 just to kind of highlight some things. The results for the other methods are similar. So along the x-axis here, we have accuracy of the base system. So this is how well the original system that I showed you is doing in this classification task. And vertically, we have the alternate system. So over here is the accuracy of the LRU system, and over here is the accuracy of the FIFO system. So each point represents how well how well the base system did at classifying this point, and how well the alternate system did at classifying this point. Again, the blue points are the profiled user. So here's how well each system is doing at identifying the real user, and the red points are again our imposters. So this diagonal here is the ISO performance curve. So this is points falling directly on the diagonal are where each system did equally well on that point. When a point is to the right of the diagonal, it means that the base system did better at classifying it. And when a point is above the diagonal, it means that the alternate system did better at classifying it. Well, the really dramatic result in this plot is that we have this really clear separation. We have all of the real user points down here. The base system is doing much better on all the real user points, and the alternate system is doing much better on all of the imposter points. This is a kind of interesting result, and we kind of have to wonder, why do we get this perfect separation? Well, it turns out that if you look at the decisions that the various systems are making, what's happened here is that these alternate systems, LRU and FIFO, have kind of learned the wrong thing in this case. They've learned the generalization that everybody is nobody is the real user, so everybody is an imposter. Okay, well, that's really good when you're in fact dealing with an imposter, because it means that if you're actually dealing with an imposter, great, they have a much higher chance of identifying that. But when you're dealing with the real user, this is bad. If we have this bias saying that everybody's an imposter, including the real user, then we're throwing a lot more false alarms than we need to. So, this is really kind of disconcerting, because learning the wrong thing is clearly not what we want to do. Fortunately, there's an alternate approach to this. Instead of doing utility-based instance selection, we can do what's called clustering, where rather than trying to remove low utility or non-useful points, we're trying to remove repetitive data. So data that we already have represented in the instance base somewhere. So we're going to group points according to some global measure of similarity, where this notion of similarity is in terms of that string matching function, that quadratic string matching function I talked about earlier. And then we can represent a cluster by a single exemplar and throw away everything else in it. So here we have a kind of example. We have this smear of data, which can actually be represented by these 3 clusters here. And now you can choose just the center point of each of these clusters to maintain and throw away all the other data in that cluster, which gets us a lot of data savings. Now, as opposed to the utility-based methods here, this is employing a similarity only among data within the profile. We're not using any external data. And of course, there are a number of different ways to do this. I looked initially at a method called case centers, which is an instance of a very popular class of learning techniques for clustering, a class of techniques known as expectation maximization algorithms, which are basically doing a model likelihood search. They're doing a gradient descent on a model likelihood space, and they're trying to locate k different clusters simultaneously by tweaking a bunch of parameters simultaneously. And a couple of characteristics are that all points in the data participate in some cluster. So after the clustering process, every point that we started with has to be in some cluster. We can't have any outliers. And that we have to know this value k, the number of clusters we're looking for, up front. So, but there's this real question, like, how many clusters are you looking for in this data? How many, kind of clumps of behavioral types? How many different types of behaviors do you exhibit? Well, how do we know this ahead of time? Well, we don't. So there's another way to approach this. It's a kind of greedy clustering algorithm that I developed for this domain, which is attempting to build clusters sequentially. Rather than trying to get them all at the same time, we try to build, we try to find the best cluster we can now, the smallest, most compact cluster we can at the moment. And then we go on and build a second one, trying to keep it far from the first one. So what we're trying to do is minimize the within cluster distance, maximize the between cluster distance. So we're trying to look for a lot of small, compact clusters that are well separated in space. And we can, we repeat this process until we can't find any more good clusters, where good means small and compact. But this means that we can halt before actually having glommed up every point. So we're going to have some points left over that aren't included in any cluster. These are outliers, and we're going to keep them in the final model. And this means, of course, that the number of clusters isn't predetermined. It's determined only by this halting criteria, which means that we're searching for it rather than having to know it up front. Well, so how well do these things actually do? So here again, we have the same kind of scatter plots I showed you a couple minutes ago. Again, on the x-axis, we have the base system accuracy. And vertically, we have the alternate system accuracy. So here's our greedy clustering method, and here's our case centers clustering method. And again, we have the same red and blue points scattered according to how each system did on that particular task. And the observation here, it's clear that these aren't doing the same thing as the methods I just showed you before. We're not seeing that very, very clear separation that I showed you before. We're seeing a lot of fuzziness. Points are falling kind of on both sides. Sometimes, this method is doing better, and sometimes this one's doing better, but it's not this clear-cut separation. It turns out that if you look at the statistics, the alternate methods, greedy and case centers here, are actually doing slightly worse than the base method overall aggregate. But they're doing it in a much nicer way than the systems I showed you previously, the utility-based systems. They're not learning this incorrect generalization. They're not trying to believe that everybody is an attacker. They're actually kind of degrading gracefully. So as you throw away more data from the database, from the instance base, their performance is kind of degrading uniformly across the board, which is really the behavior we want. So how well do these two clustering methods do against each other instead of against the base system? Well, there's a ton of points on this. This is on the Calgary data. The last one I showed you was on Purdue data. So we have these thousands and thousands of points here, which I chose to highlight this mass. I hope you can see. Some people say it's very evident. Some people say it's not. That there's a lot more mass of the red points on this side of the line. Well, what we have here is the greedy system on this axis, and we have the case center system on this axis. And the two are set up. The parameters are chosen such that they are achieving the same level of data compression. So the two systems are comparable. But there really is this enormous amount of mass, at least at the red points on this side of the line. Statistically, the greedy system is doing significantly better than the case center system in this case. When it comes to the blue points, so the red points are our ability to catch an imposter. The blue points are our ability to recognize the real user. If you look at the statistics there, it turns out that the two systems are not statistically distinguishable with respect to detecting the normal user. So if all you're worried about is detecting the normal user, then it really doesn't matter which of these two systems you use. Of course, if all you're worried about is detecting the real user, you shouldn't be using one of these things all the time, at all. You should just be saying, oh, it's the real person, no problem. Well, this looks very nice. It looks like, oh, great. Well, what we want to use is this greedy clustering method all the time. Unfortunately, of course, in reality, there's always a catch. And that catch here is that this is kind of a snapshot at about a 67% level of compression. So we've thrown away 67% of our original data. That turns out to be about as much as the greedy system can achieve on this data. For algorithmic reasons, it's limited in what compression levels it can achieve, and that's about 71% on this data is as best as it can do. The k-center system, you can just crank k lower and lower. K represents the number of clusters you end up with, but that in turn is the number of final points you end up with. So you can crank k down to like 1, and have 1 over 1,000, data compression. So if you want to achieve much higher compression levels than greedy is going to give you, you're going to have to go to the k-centers system in this case. And so that's kind of, the conclusion for this section is that if you're doing instance selection in terms of this utility-based selection, we get this nobody is the valid user problem, at least for the methods we've tried here. The clustering methods don't do that. The greedy system works better over a limited range of compression, but k-centers can really get to a much higher compression level. So let's see, how am I doing on time? Whew, okay. It looks like I'm not going to have time to tell you much about the concept drift work. If you're interested in that, you can see me afterwards, or I can point you to some papers. But I will get into an alternate class of models that I've looked at, these hidden Markov models, which I mentioned earlier. And so for those of you who may not be familiar with these, you can think of an HMM as just being a statistical model of sequential data. And, because, if from a computer science background, you may be more familiar with finite state machines, so you can think of this as kind of a stochastic DFA. So over here we have this 3-state state machine with these stochastic or probabilistic transitions between the states. But an HMM is a little bit more than that. It's doubly stochastic in the sense that you don't get to see the state directly. You don't have a state emitting a single token. Instead, each state is associated with a distribution over tokens. And at each time point when you look at the machine, what you get out is not this state, but something drawn according to this distribution. And what this allows us to do is to represent different behavioral contexts. So up here, if you can read it, we have a lot of weight up here on the commands ls and cd. So this state might represent somebody navigating through directories, whereas down here we have a lot more weight on the command vi, which means, down here the person may be, editing something. So the number of states we have here, what I'm going to call the order of the model, or a parameter k, represents the kind of number of behavioral contexts I can represent with this model. So the more states I have, the higher order model I have, the more behavioral complexity I can represent. And these models are really nice because there's a lot of very nice tidy mathematical ways to learn all of these values and to construct these things, and they have a very nice representation for doing online learning, so allowing us to learn continuously. So how does this change the detector system that I've told you about? Well, not a whole lot. We still have the same data entering, we have the same tokenization, but down here, rather than an instance base, we have one of these HMM models, and now we can, the similarity is no longer the string matching function, but it's a likelihood evaluation. So the likelihood of this data with respect to this model, it actually takes place on a log likelihood scale. So, here's this sequence of likelihoods over time. We smooth it with a mean, which gets us from instantaneous log likelihood to kind of long scale likelihood. Yes?
Is this likelihood multidimensional? As many models that you can have in as many states as
no, it turns out that you can, what you do is you conglomerate all of the likelihoods that each state produces into a likelihood for the single model. for the entire model. At each time step, you get a single likelihood value out. And then this mean allows us to accumulate multiple time steps into a single likelihood over a window. And so if you are familiar with HMMs, you can think of this stage from here to here as kind of being the forward step of the forward-backward algorithm. Classification is the same thing I was talking about before. We use the same kind of threshold test, only we now interpret it in terms of likelihoods rather than similarities. And again, there's a feedback loop, but this time it's dotted because that's future work. That is, I haven't written the code yet. So the results on this are less well developed than what I've shown you before, but I can show you a couple of interesting points which really motivate some of this work in the HMMs. So I've picked out a couple of individual users here. So users number 4 and 7 from the Purdue data set. So these blue points now just represent this one person as opposed to all the different users that I had available. And the red points represent all of our Purdue opponents. So again, we have these comparisonal scatter plots. Only now on the horizontal axis, we have a model of order 50. So this is a machine with 50 hidden states. And on the vertical axis, we have a machine with only a single hidden state, which, if you think about it, a single hidden state is equivalent to making a multinomial model of the data with kind of no temporal information. So it chose these two users to demonstrate a couple classes of behavior or an interesting difference. The first is if we look at this user over here, we see that the simple model is doing very well at distinguishing the opponents. It's picking off the opponents very well. And it's not doing too badly on picking off the normal user. We have this big clump. Most of the data is up here, clustered very close to this equal performance line. So our simple model is, a great detector for our opponents and not too bad a detector for the real user, with the exception of this one little cluster I'll talk about in a bit. Over here we have a quite different situation. Here we have that the highly complex model is doing much better in all cases. We're doing, really great at detecting our opponents all down in this region, and we're even doing better up here with detecting the real user. Well, what's the explanation for this, and why is it so neat? Well, if you look at what these two people are actually doing, what their actual data looks like, you see a big difference. This user's data is very, very simple. Behaviorally, is that a question or no? Okay. Oh, please. Oh, not a difficulty. Yeah. So this user's data is very simple to look at. In fact, what we're seeing here are things like 1,000 instances of GCC in a row. Obviously, this guy had a lot of bugs in his code. This data is a lot more complex. Here you're seeing multi-stage pipelines. You're seeing looping control structures at the command line. You're seeing, Perl shell scripts being written in the command line, things like that. A lot more complex data. This is me. So what this tells us, this is kind of a correlational result rather than a causational result, but what it tells us is, or what it suggests, is that there's this correlation between the complexity of the user's behavior and the complexity of the model needed to represent them. So over here we have simple data, simple model represents it well, with the exception of this one little cluster down here. And if you look at this, in fact, you find out that this is the person deviating from just typing GCC and typing, a few other commands as well. So here you might need a little other, model complexity. Over here, very complex user behavior, very complex model. What this suggests is that if we can now detect the order of the model that is appropriate for the user, then we have a way to detect the user's behavioral complexity, rather than having, to go the other way. And I think I can do that, but that brings us to future work. Where I'm going now is to build adaptive statistical models. They can model non-stationarity. So you have these models that are continuously learning rather than training in batch mode, as a lot of what I showed you here was. They can continually update their parameters. And in particular, I'm looking at class of models called single-step recursive updated HMMs with order identification. And this with order identification here is the part that means that I can maybe detect online, or as it's running, how many states I actually need to model a person, how many classes of behavior they're exhibiting, how complex their behaviors are. And that means that, maybe I can, dynamically, as the system runs, detect how complex a user is sitting at the terminal. And this is, this could be very useful too, in this task if I can, if I have a, two-state person, some freshman who's just come in and only knows how to do, email and read news at the moment, and all of a sudden it jumps up to like an 83-state model person, then that's a pretty good sign that there's something funky going on. I'm interested in doing feature subset selection. What this means is, through this entire talk, I've been talking about one data source. I've been talking about shell command line data. But clearly, there are hundreds, if not thousands, of other possible data sources that you could look at. There are, memory footprints and time of day and, typing rate and GUI events and mouse clicks and all sorts of things like that. A lot of people have proposed using different ones of these features, but I haven't seen a good comparisonal study which tells us which of these are actually useful to use. So that's something I'd like to look at. I'm interested in multi-sensor integration so combining these kind of models that I've got with other models monitoring the user to yield a kind of better overall estimate. There are a lot of results in the machine learning community which tell us different ways to make these kind of combinations, models like boosting and meta learning. And within the security community, there are a lot of systems or a lot of projects ongoing at the moment to develop these multi-sensor hierarchical detector systems that integrate a bunch of data sources. So here at Purdue we have APHID, and SRI has Emerald, and there are a couple of other projects ongoing that all use this idea of multi-sensor integration. And of course there are other models still to look at. I've showed you two today. I've showed you instance-based models and HMMs, but they're both effectively Markov in a statistical sense, or what you might think of as being somehow equivalent to a finite state machine. But you can step beyond that to context-free grammars or even probabilistic context-free grammars. There's a class of models called a Bayesian inference net, and there are still others to be examined. And of course I'd like more data to do this on, and currently working with Diego here to, and hopefully some of the students in CERIAS to be able to get some more data to test this on. And of course I'd like real attack data if I can get it. So if anyone happens to have a recording of some hacker coming in and trashing your system, I would love to have it. Yeah.
Consider setting up a system and inviting people to it?
Yes, actually that's been suggested a couple times, and I considered doing it, and I asked Spaff, and he's like, oh no, you'll just get posers if you do that. Let's not open up that can of worms. So I don't know. Yeah, I think what I would like to do in the short term is ask local people, actual security experts, to try to attack it rather than just anybody in off the net. I'd like to get some people here in CERIAS who actually know what they're doing to try to attack this and see how well it stands up against an actually determined attacker who knows that the system is present and understands how it works. But yeah, clearly there are some things you could do to try to get real data, or at least semi-real data. So, and I should also insert kind of here at the end that this can be used for more than just anomaly detection and for more than just security. We can use it to do skill assessment, especially if we can detect the user's behavioral complexity. We can do, maybe automated tutoring or automated help systems, hopefully better than the Microsoft paperclip. Stepping back from users, we can perhaps identify people as being members of groups. So I can identify that you're a programmer, or you're sysadmin, or you're whatever else, and then be able to suggest tools or help files or other documents that have proven in the past to be useful to that user group. Or I can step down from users to behavioral identification, so I can identify what particular types of behavior you're doing now. You're editing now, or you're compiling now, or you're surfing the web now, or whatever else. And maybe behavioral prediction, which should allow us to do things like web prefetching. If I can predict what, if your browser can predict what web page you're going to go to next, what link you're going to follow, it can preload it for you, which is going to save you the network latency, or at least hide it from you. Another idea that's been recently suggested to me, which I think is really neat, is to do workload generation. So if I have a good model for how people generate data, I can run my model generatively to produce data in the same way that they would, to produce keystrokes and commands the same way they would. And this is useful for software testing. If I can generate, say, GUI events in the same way that a user will, I can throw this stream of GUI events against your program that you're developing, and you can find out where it crashes without having to have a dedicated software test person sit down there and click on the thing a million times in a row. So I guess that's what I have to tell you about my work, and that's kind of where I am. So are there any questions about it at the moment? Yeah?
How effective would this be if like an attacker would log on, have a history or whatever to find out what the user uses, and then what directly made you said it's fine, but the attackers like to meet up very often, so they make a script all the time. They can alias kind of all the commands they want to do under the command name fine. Could that avoid, if your local records would have before?
Right. Well, in the way that I'm actually gathering the data right now, which is using the shell's history mechanism, clearly that's kind of going to bypass it, and so would scripts, so it can attack scripts. But you can step down a level and actually catch the exec system call and trace what programs they're actually executing, which introduces a new set of difficulties. But there are things you can do to that particular scenario. So I mean that's also kind of the scripted attack scenario, right? So, other questions? Yeah.
Okay, you say it's a user assistance program, right? Like
Mhm.
the user is going to run it.
Hopefully, yeah.
Yeah. How does that? Or I mean, is it like set UID root or something so that when if an attacker logged in, PS, and hey, there's that detection program and kill it off, or I mean.
Well, again, now you're getting into the non-naive attacker scenario, but clearly there are all sorts of things you can do. You could make it SUID, or you could make it part of the kernel potentially, or some loadable kernel module running on some. Let's say there are things you can do to hide things within the PS traces and stuff like that. So sure. I can't, I'm going to tell you up front that this is not going to be a perfect answer, right? There's always going to be an attacker determined enough and knowledgeable enough to be able to defeat it. But what this is going to do is hopefully be able to catch, a large proportion of non-knowledgeable people. And there are plenty of those out there to catch. I think I heard an estimate that CERT estimated that something like 95% of system intrusions are never even detected, And if we could detect, half of those, we'd be doing a great service, right? Mm-hmm. So, any other questions? Okay, well, thanks very much for your time.